This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Hi everybody, good afternoon. Just before we start, just a quick reminder, the Friday lecture and tutorials have been rescheduled, so we won't have any lecture or tutorials this week. They have been rescheduled to the first week of October, just after the mid-semester break, and there is an announcement on the LMS, just to make sure nobody rocks up, okay? And today we're going to talk about indexing, which basically deals with information retrieval. So how do we access quickly and efficiently data from large databases? And just to start with, let's start with a very simple, very broad metaphor. So we have a lot of data, and we've been accumulating data over the years. So you are in a library, and you need to find a specific piece of information. And the main problem is we have too many books. Too many books, not enough time. And books contain the information you want. And basically, the question we want to ask is, how do we find the information we want? And how do we do it quickly? And in order to do that, we need to organize our data properly. And for instance, our data could be in, let's say, in a library in Victoria, but which one? And so we're interested to know and understand quickly how to access the data, for instance, which library it is, which book it is, which chapter it is, and more specifically, which page. We don't want to go to every single library to check for every single book, every single chapter to find the information we want. How do we go from a given information to actually its location and its content as quickly as possible? And this has to do with indexing. So we will use this book library information metaphor throughout this lecture. So basically, the question we want to ask is how to organize information efficiently in a way that we can retrieve it quickly. And now imagine that libraries don't catalog any of their books, either by title, by author. They don't catalog, they don't organize, they don't sort their books. Imagine how difficult it would be to find information. And imagine if they do organize things, let's say they organize by something that is not very practical, let's say the ISBN number. So ISBN is a unique identifier assigned to each published book. Let's say you have a bookshelf there, organized by ISBN, and you have a book title. How are you going to find it? You need to go through every single book, potentially, to find the information you need, and that's just not going to cope. So that's not efficient enough. So let's say things are a bit better organized, and they're organized by title. Even if we organize things by title, we need to identify which aisle we need to look for, which shelf we need to go, and we still might need to go through a subset of them to find information we need. Can we do better? That's the main question here. And that has to do with the data structures we use. And today, let's imagine our library as a data structure, okay? And there are different ways to organize it. So we have a collection of books, and we want to organize it in the best way possible to identify and access information from it, okay? So let's consider our library, our collection of books, as our data structure. And the first thing we need to think about is which data structure to use that will help us access information quickly. Okay? Let's start with a simple one, a list or an array. So if you think of an array, you access an array by position. So you want the first index, the first element, or the last element, or the kth element of a list. Okay? Let's say we're organizing our books in a linked list. So we can access the first. We can't see the global structure. So for instance, if we're looking for this red book by a title, we would need to eventually iterate through it to find it. So let's say we search a book by title and we have a linked list. How long does it take? What's the time complexity of searching on a list? ON. Yeah, so worst case scenario, we need to check one by one, is this my title, is this my title, is this my title, until we find it. Okay, so this is not very efficient if you have too many books. Can we do better? So let's try to find out a different data structure that will render better results in terms of search time. What could it be? It could be a tree. Instead of a tree, so tree is for next lecture. So let's try just sorting out this array. Same old array, but it's sorted alphabetically, lexicographically, numerically by ISBN, but it's sorted. Okay? How do we search for the information on a sorted array? And that's, well, we'll try to use a different analogy here. And the analogy is the following. You have a company that builds impact absorption material, like for running shoes and so on and so forth, and you want to promote it with a really nice ad where you're in a 100-story high building, you drop an egg, and it absorbs the impact, and the egg doesn't break. So let's consider a 100-story building or case-story building, and you want to ask the question, at which floor the egg will break, okay? And you want to find the minimum number of attempts as possible. So how many attempts do you need to identify which floor exactly will the egg break, considering if it breaks on the 10th floor, it will break on the 11th, 12th, and so on and so forth, okay? And you don't want to waste eggs, and you want to try as minimum times as possible. So for a 100-story high building, how many attempts do you need to find exactly which is the floor that the egg is going to break?
6 or 7.
6 or 7. Why is that?
You just checked in the 50th floor if the egg break.
Yeah? So you try on the 5th floor. If it breaks, yeah?
If it breaks, it must break over the 5th floor, 50th floor.
Yes. So if it breaks here, it's certainly going to break up here. So we don't need to search that. Right?
Yeah.
And go on.
And just iterate it.
Iterate dividing it by 2. So what you described is basically called binary search. Right? So since we have something that is ordered, so each floor on top of each other, and considering if it breaks on the kth floor, it will break on the k plus 1, plus 2, and so on and so forth, we can divide the search space every time by 2, and that's what's the time complexity of searching that. It's logarithmic, right? So since we're doing that, dividing the search space by 2 every time, so the number of times we need is log 2 of the number of floors. So for 100, log 2 will be 6 point something. Let's say the minimum number is 7. And the same thing for your books. So if the books are sorted by a given criteria, we can do binary search and find the book we want in logarithmic time. But if you have too many books, that still might not be good enough, especially if you need to do this operation over and over again. Let's say you need to do this hundreds of times or millions of times. So again, the question, can we do better? And we do that basically with indexing. So the indexing concept is basically, and you can do binary search to do that, but the indexing consists of a mechanism to speed up access to a given desired data. So it has to do with information retrieval and how we do it as quickly as possible. And the concept of an index is basically has 2 components, a search key. So for instance, if you look at an index in a book, you're interested in a specific term, and it gives you at a constant time automatically where it is. Okay? So you have a search key, which is an attribute or a set of attributes used to look up a record in a given file. And the other part of an indexing is the actual index file, which basically consists of records, your actual data, let's say it could be, but for instance, text, biological data, that is indexed by a search key. Okay, so it's a pair, search key and value. And here we'll discuss a few different ways of indexing or generating this index and how it can be used in a real-world situation. And we'll start with the idea of indexing a genome. And that's quite important for the BLAST algorithm. If you recall from week 2, if you don't, I don't blame you, it's been 7 weeks. So let's look at indexing a genome. And this indexing will allow for fast lookup of subsequences in this genome. And this is extremely important for high throughput sequence alignment. this is actually one of the first steps of the BLAST algorithm. And the main motivation here is make the alignment of millions and millions of strings of reads, let's say for NGS, feasible. Okay? And indexing algorithms are also related to data compression. And on the next lecture, we'll talk about Burrow-Wheeler's transform, which is used for the algorithm bzip2, but it also allows for memory-efficient alignments as well. So if you recall, the first thing BLAST does is creating an index of all the k-mers of a given size, looking at the database and your query sequence. So you can ask really quickly whether a k-mer in a query sequence appears anywhere in the database. And from there, you can do then extend the alignments. So that's the clever thing about BLAST. It doesn't need to do alignment over everything, so it starts from the seeds, so the matches between k-mers in query sequence and the database. And it does that really, really quickly by an indexing approach. So for pairwise alignment, if you also recall optimal pairwise alignments, these are done by dynamic programming algorithms. We discussed two of them, one local and one global. Local Smith Waterman and global Needleman Wunsch. So they're both dynamic programming approaches to identify the optimal pairwise alignments. And as dynamic programming approaches, their time complexity is basically related to the length of sequence 1 and sequence 2, which will need basically to fill up a matrix. So they run in quadratic time. Okay? And that's basically impractical if your sequences are too large, too big, or if you have too many sequences. For instance, the human genome sequences is 3 billion base pairs. And for instance, if you are aligning reads from next generation data, if you recall, for next generation data, the approach is we can't sequence the whole genome at once. There's no technology capable of doing this, so we chop it up in very, very small parts and read all of those parts. So we read millions of short sequences, and we need to align them to a reference genome. So we talked about this. Actually, Simon talked about this on the novel genome assembly. So we're doing an alignment of a really short sequence, let's say 300 over 3 billion base pair. And if we do this with optimal pairwise alignment, this will take each time quadratic time to run. We'll need to repeat this millions of times because from NGS, we'll get millions of reads. And again, what we need here is basically heuristics to speed things up. And that's what BLAST does. And the main thing that makes BLAST run quickly is the initial step called seeding detection, which is done via indexing. So indexing BLAST is used to identify likely alignment sites. And these are based small near exact substring matches, which are called seeds. And these are basically on the dynamic program matrix diagonal stretches that we have a lot of matches. And one way to identify them is basically using indexing. And the approach for BLAST is just doing the full alignment on those seeds and selecting then the best scoring alignments out of those. And the main benefit of this is the exact or near exact match can be done really, really easily and fast with an indexing approach. However, the trade-off, of course, since this is heuristics, if we don't get a near exact seed match, we might miss good alignments. But then we'll speed up the process, okay? So we can't guarantee the optimal solution, but we'll have a trade-off in terms of running time, which will be reduced dramatically. And the way BLAST will find the seeds is via indexing. So first thing it does is for a given database, it will split it up in k-mers. So we'll run a sliding window on every sequence on our database, and we'll map this to a dictionary. Bear in mind what's of this word, and we'll discuss the meaning of this. And we'll do the same for the query sequence. So we'll break it up in k-mers, and our main goal here is to find a function that maps what I can see from the query to what exists on the database of sequences. So seeds in this case are small subsequences of our initial sequence that are equal, identical, or almost identical to the reference. And we'll use an index or a dictionary to find this mapping between query and database. And the main principle here is that the index will allow a fast lookup time of these seed strings rather than doing the full optimal alignment. And an index of the reference genome then can be computed and pre-used. So once we calculate our index, which are basically then the search keys and the values, and we do that, let's say, for a database of sequences, we don't need to do that again. And we can just look it up when necessary and just perform it for each querying sequence we need, which is one of the advantages. And in this case, and for BLAST, the index query database is based on k-mers or words of a given size. And of course, there is also an issue with seed feasibility, as NGS data can have errors. And every error in a read, let's say you have a read of size n, your k-mer is size key. So a read in a given position can affect up to k-mers. If we have on average on total e errors introduced, this will affect k times e k-mers. And out of the total number of k-mers in that given read, which is n minus k plus 1, we can calculate then how many error-free k-mers there is, which is something like this. And this is being affected by the number of k. So what's the size of my sliding window? And even though smaller k values will have a large proportion of error-free k-mers, longer k-mers will mean less matches on our matrix, less extensions that we need to do, but less error-free k-mers in the sequence as well. So we need to balance them out. But as we increase the number of k-mers, the potential number of mappings we need to do increases exponentially with its length. So 4 to the k's, where k is the size of the k-mer. So it's something we need to bear in mind when selecting this. And this has to do with choosing an adequate data structure for the indexing. So getting back to our analogy of the library in the books as our data structure, we talked about lists using a list of an array, a linked list, for instance, an unsorted list, which would render a search time that is linear. We can improve this by using a simple sorted list, which would render then logarithmic time for search, but we still can do better. And for different circumstances, we need to choose what works best, and we'll discuss a few of them here. And the first one is hash tables, a very, very interesting data structure that's used in BLAST, but also there are suffix tries and trees, suffix arrays that we'll discuss in a few weeks, and also the FM index and the Burroughs-Wheeler transfer, which is also important for data compression. But before we start talking about hash tables and how we go from logarithmic time complexity to constant time complexity, let's just get back to binary search first. So we're interested in doing k-mer indexing, okay? And we want to store k-mers of length k and their positions in the sequence. And the first idea is to create a pair, key, and value. So what is the k-mer and where it appears in a sorted array, okay? It will look something like this. Let's say we have our sequence, which is this one here, and we want then to go through a sliding window and keep inserting them in a sorted array. So let's say our first k-mer is GTG, and it appears on index position 0. We put it there on the array. And let's say our array is sorted lexicographically. First up, we move the sliding window. We have our next k-mer, TGC. We add it lexicographically, so it will be here. And this is in position 1. And we continue that process for every possible k-mer, which takes, again, linear time. So I'm moving down the sliding window one by one. And then we have our k-mer index, which is basically an array with the sorted k-mers, observed k-mers in lexicographic order and where they appear in the sequence. And then we can ask the questions where a given k-mer appears. So just to simplify, to exemplify how binary search would work. And it would work as follows. Let's say we have our database of sequences, and we created the index for these one, and we have a query sequence, and we want to ask the question, does GCG appears here, and where, and how we can find it very quickly. So what binary search would do is basically, since this is sorted, I'll start in the middle and ask the question, is the k-mer I'm asking for, GCG, lexical precedes the middle k-mer or not? If it precedes it, the k-mer I'm looking for is in the upper side, otherwise is on the downside. And so basically we're creating bisections in the data each time. So for this first bisection, we find out that this k-mer is on this side. So next up what we need to do is, considering the upside, I'll then ask which is composed by these 5, as we can see here. We ask the question then, if we go to the middle again, which is GGG8, we ask the question, GCG comes before or after GGG? And then it comes before. So we divide the data set again, and then we have these 2, and then between them, we find that it actually happens here at index 2. Okay? So GCG. And of course, since we're dividing the search space by 2 every time, the number of bisections we're going to generate equals the number of times we need to iterate to find a given element, and that's logarithmic. But let's write something slightly more efficient. And for that, we'll need a very interesting data structure called hash tables or dictionaries. So a hash table is a data structure for indexing composed of 2 different parts. An array table that will be the analogy of our bookshelf. And this will actually contain the data we are interested in. And this could be sequences, this could be any type of value you want to store. And where the search will search through to find our data, and a mapping function called the hash function. And for hash tables, a hash function will be responsible for taking an input data, a key, and create a mapping by assigning it to a very specific index in the array. So if I start with a book title, and let's say our book title is our key, a hash function will create an index, also called a hash bucket. Let's say, given a title here, we have a hash function that generates the number 3, and we put our book on shelf number 3. Okay? And basically, the idea of the hash tables is creating this key and value pair through an efficient hash function. So if our hash function is efficient, we can access data in constant time. So we basically, if our hash function is O1, so it's constant time, it's just a simple operation, given a book title, we will be given an index, and we can access the book straight away. This is constant time complexity compared to our original linked list. In the worst case scenario, we would need to iterate through the whole extension of that list to find that book, which is a linear search. So just to give a really, really bad example of a hash function. So a hash function is basically mapping inputs to an index. Let's consider the modulo operation. Does everybody know what a modulo operation is? So modulo is basically the remainder after division of an integer. Okay? And then let's consider the module to hash functions on integers. And it has a constant cost, which is something good. We want something that is very quickly. So 5 modulus 10 is 5. So that's the remainder of the operation 5 divided by 10. And this number, modulus 10, is 3. So you're basically getting the remainder. So 3 modulus 5 would be 3. 13 modulus 5 would be 3. 12 modulus 5 would be 2. So the remainder of the division. And for our hash table, we'll then go back to the indexing book titles, and we'll use the modulo function as our hash function as the following. We'll define here arbitrarily, we want 12 buckets. Okay, so a hash table of size 12. And what we're going to do is we'll have a hashing algorithm that works as follows. So we'll take the number of characters in the string, in the title of the book. Let's say The Great Gatsby, which has 14 characters. And we'll divide that by the size of the table, which is 12, and get the remainder of the division as the index, which is the bucket we will put the book. So 14 modulo 12 is 2, and then we'll put the Great Gatsby at this shelf here. And we'll do the same, for instance, 16 characters, 16 modulus 12 is 4, we'll put the book here, 18 modulus 12 is 6, we'll put the book here. If we had 12, 12 modulus 12 is 0, we would put the book at the first position. But what happens if we have another title, The Old Man and the Sea, which has 18 characters, 18 module 12 is 6, 6 already taken. What do we do? So an array, by definition, is a contiguous amount, space in memory. We can't put two things in the same position in memory. We'll overwrite them. Same thing for the book. So this is called a collision, which is a very common thing in hashes. But we'll get back to collisions in a bit. First, I'd like to discuss what's a good hash function, right? So this example was not good at all. So a good hash function would have a few interesting properties. First of all, it needs to be fast and easy to compute. Basically, that's very simple to understand. If you have a really, really hard to compute hash function, let's say a hash function that is linear or quadratic even, you basically, when you're accessing your data, you lose any gain advantage for the quick lookup. Even if your lookup is O of 1, is constant time, if your hash function is complicated, you lose that time. So you lose an advantage of having a hash table. We would like then our hash function to map to a finite size output value. We would also like that it to produce a good distribution of values over the table, to avoid as many collisions as possible, because collisions, as we're going to see, deteriorate performance of our lookup time. And we also need a way to resolve these collisions, and we want a hash function that is deterministic. And that's very important so we can have an easy and reliable way to access and retrieve the data. So every time we provide a given key, we want the exact same index. So that's basically being deterministic, okay? So we can't have stochastic hash functions. And going back to collisions then, let's say we have two book titles and they need to be in the same position considering a given hash key. That's probably not a very good hash key, but there are two ways of resolving the conflicts, and this will reflect basically on the data structures we are using. So the first one is called linear probing. It's when our hash table is actually an array of a fixed length. And what we do is, once we find that this index is already filled, we just try to find the next one. So we search the table until we find the next available hash bucket, and we put the book there. So if position 5, it's already used, we'll try 6. If it's already used, we keep trying until we find one that is not in use, and we put the book there. And if we reach the ends, we can basically go back to the beginning and start over. Okay? The downside of this is basically the tendency of generating clusterings and poor distribution in the table. So we have a table at the end, if you have too many collisions, that looks like this, and ideally we want it to be very spaced out. And alternatively, we can do something called chaining. So using our hash table as a linked list. So basically we would still have a fixed number of buckets, but each bucket in this case is actually a list. So what happens if you have a collision, you basically add another element to that list instead of storing it someplace else. So what's the problem with this? Is basically if we have too many collisions, we'll keep adding elements here. So if we have a really, really bad hash function that half of the time we have a collision, we end up basically iterating through the whole data set to find what we want. So that's why a good hash function needs to minimize collision. Then, of course, the downside is more time to search, but we then try to design a good hash function in order to minimize the number of collisions. So if collisions are rare, we can say that our search or lookup time is constant time as well, O1. And just to have a really simple toy example on sequences, using this type of structure. So in this case, our hash table is of fixed size, and we're using each bucket as a linked list, okay? And let's say our hash function is called h, and we're going to map k-mers of size 3 to these buckets considering this sequence here. How this is going to work is the following. So we start with the first k-mer, which is GTG, and we ask the questions for a given hash function. So this is not modulus. This is obviously not modulus because our k-mers have the same size. So we need a different hash function that it will spread those possible k-mers in the different buckets. We're not going to talk about this hash function. It could be different approaches. So consider you have a good hash function. And we'll submit this k-mer to this hash function, and let's say it says, well, you need to insert the k-mer GTG in this bucket here. And we insert it as an element of a linked list, and we start, okay, GTG is here, its index is 0. And this is the end of the list, so there's only one item on that position. And we move to the next one. So the next k-mer is TGC, and the hash function decides that it goes to the first bucket. We add it there. This is the second k-mer on our string, and we keep going. So the third one goes here. That's the index 2, GCG. And the next one goes here. And next up, what we have is a repetition. So depending on how you implement your hash function, you can have different things. In this case, since we're considering a sequence, and for the purpose, for instance, of applying BLAST, we would like to keep track of all positions, so where a given k-mer appears. So this is not actually a collision, because it's just the same k-mer appearing 2 times, the GTG here and GTG here. So, but let's keep track of where they appear in the sequence for the sake of applying it for high throughput sequence alignments. So we just add it to the linked list and saying, it's the same one, it's not a collision, but it appears then on position 0 and position 4. And then, let's say we get to TGT, and the hash function sends us to this bucket, but is already filled up with a different k-mer. This then is a collision, and it's inserted there where the position happens. And the algorithm keeps going. So I have another repetition here, and this is a new k-mer, and another collision here. It will be inserted, and so on and so forth. More repetitions, and we finish indexing our sequence with this hash table. And hopefully, given that, considering that we have a good hash function, this hasn't deteriorated too much our ability to find information. And let's say now that since we have an index for a given large sequence, we can ask the question for a given query, GCG, where is GCG? And we basically do it very quickly by just calculating the output of the hash function, and it goes to this position and this bucket, and we just need to iterate through the linked list to find it. And ideally, we won't have too many collisions, so this whole process will be very, very quick. So ideally, we'll still have a lookup time on average that is constant time. Okay? And hash tables in Python, I'm sure you all used it for the assignments. So they're usually called dictionaries or maps. And they will then store keys and values. But also Python has something called multi-map, which will allow you to store multiple values per key. And in different languages, this will vary. For instance, you can store numbers, you can store strings, different types of data structures, and even objects. Okay? And this type of object here, dict, will have then a key that will be looked up in constant time. And you would look, the syntax will look something like this. So if we have an initial sequence and we run the k-mers, we will have a dictionary or a hash table that would look like this, with all the appearances of a given k-mer, and then we can ask the question in O1 time, in a given table, where does GGG appears in a sequence? And it appears in 3 positions, index 8, index 9, and index 10, basically here, here, and here. And this is, of course, this is very important for BLAST and and high throughput local alignments. So just a brief summary of hash tables then. So they're very, very important data structure. And if we want to, let's say we want to index k-mers for a genome of length m, in terms of time to build, since we're going to have to iterate through the whole length to generate the k-mers, that's linear. So we'll take linear time to actually generate the index, but once it's generated, we don't need to do it again. That's one of the advantages. And the main thing for hash tables is a quick lookup time, ideally O1, if we do have a hash table, a proper hash function. And in terms of a space requirements, again, it's proportional to the size of that genome. But the problem is we can only look up exact keys of length k. So what if we have mismatches? What if we don't have, we need to allow some sort of variance in our keys? Then we can't use hashes. And we'll discuss alternative data structures on the next lecture, how to encompass mismatches as well. And then, just to recap, a good hash function will then have a few properties. So it will generate well-distributed indexes, and that's very important to avoid collision. What collision will do is deteriorate our search time. What else does a good hash function need? Let's see how your short-term memory is. What else do I need in a good hash function? It needs to be fast, and what else? Deterministic. So I need to be able to repeat and for the same key, always generate the same index. But one thing to keep in mind, while an array in memory is ordered, so you access it by an index, a hash is inherently unordered. So we don't know how this is stored in memory, and it doesn't matter, okay? As long as we have a quick way to access the data. So it's not sorted in memory by definition. And from not next week, so on the 7th, we'll talk about different ways to index data, and this will involve suffix tries and trees. We'll also talk about suffix arrays, FM index, and other approaches that are important for data compression. Okay? This is all for today, and assignment 2 will be released hopefully tonight. Worst case scenario tomorrow morning. Okay? Thank you very much.
We post these keywords in the last just around the lay.
Oh, sorry?
Why we posted this in the first?
Why not within the first? Yeah. Thing is, let me just take this off. What happens is, can I? Yeah. So what happens is the following. So we have this hash function here.
Yeah.
We don't know what h does. Let's consider a very, very clever way. So a very clever way of giving an input, let's say we have a TG here, it's going to generate an index here, right? But we don't know what h is. So the purpose of this is not describing how good h is. H is just a given hash function, right? So it's basically saying you need to put it here, okay? Okay, for instance, I can give you an example. This might not be the case, but for instance, each character is encoded in ASCII as a number.
Yeah.
So let's say A is 60, B is 61, and so on and so forth. And let's say we multiply them. So T, which is, let's say, is 90 times G times C. And this is our hash function. Okay? Let's consider we use this. But it doesn't matter. This is not important. The important part is, given that our hash function sends TGC here, what do we do? Okay? But we can have different hash functions, and they will work differently. Okay?
So in this one, the hash function is T times G times.
It isn't. I'm just giving an example. Okay? It could be very, very clever ways. You could use an algorithm called an MD5 as well. Have you heard of MD5? So different, we'll mention that, but it's a different way to convert a string to an actual number. There are different approaches to do that. We won't touch on the actual hash functions because there's a lot of theory behind it. Because if you think about it, you need to basically do a mapping from anything, let's say a string, any given string, to something that is really, really well distributed. So it's a very, very complicated thing to do. But there are standard hash functions. For instance, Python implements its own hash function, which will be different from Google's hash function, and so on and so forth. Okay? So this is not, for this example, this is not actually relevant. So just considering I have an input is a Kmer, and I get an index as an output.
Yeah.
Okay?
Yeah. And so in the so this one is because of the hash function.
Yeah, so for some reason, the hash function decided, well, when I calculate the hash for this and this,
Maybe the two cameras have the same features.
yeah, or the way it's calculated, or it's just a limitation of the hash function. That happens. So collisions happen, right? We want to minimize it. So a lot of people invest a lot of time in PhDs, theses, and all that, how to come out. A long time ago, not anymore. This is a solved problem on how to come up with good hash functions, right? But there is a limitation of them. So if you have way, way, way too many items to index, let's say you're indexing things on the scale of Google, billion and trillion, Python hash function is not going to work. Okay, because you start having too many collisions. Then you need, perhaps, if you have too many data points, then you perhaps need to think about alternative non-standard hash functions. But most high-level programming languages will have theirs built in, so you don't need to actually implement it. Well, I had to when I did my undergrad, but and then, for instance, you can assess how good your hash function is basically on the number of collisions or how much memory you require, right? So if you keep track of how many collisions you have and you have different test cases, then you can say, okay, maybe this is a good hash function, this isn't a good one, and so on and so forth. Yeah, so this collision is basically because of this hash function decided, oh, they need to go to the same place. There was already one there, and we just keep track of it. And if we have another one, we create another one here, and another one here, and so on and so forth. Okay, but that's different from this. Okay.
It's a repeat. Just we can combine them.
We can. I mean, depending on the application, this is important for blasts, keeping track of every single occurrence of the Kmers, right? On a standard Python, this wouldn't be here. They would be overwritten because it's basically saying GTG is on position, let's say 10, and we'll say again GTG is already there. It's 10 again. So it wouldn't include another one. For these purposes, it will. Okay, because we're interested in where it appears. So it appears on 4th and index 0. Make sense?
Yes. Thank you.
Not a problem.
Thank you.
I just want to ask about the accessing of the hashed array.
Yeah.
So when it is when you stack them, like if you have a collision, you push the content down one bucket.
For instance, like this, you have this, you need to include another one, right?
Yeah.
It's a list. So with a linked list, you can implement different data structures. You can implement a list, you can implement a stack, you can implement a queue, and the difference between them is where you insert, where you remove, right? So for instance, in this one, it's inserting GTG again. So where it's inserting is inserting the beginning of the queue. So usually on a linked list data structure, you know where the beginning is. You have a pointer saying this is my beginning, this is the end, and you have the links between each of the nodes. right? So if you need to insert something, you can either say, well, it's easier to, the actual operation, if you implement it on a, do you have paper? Yeah. So if, let's say, you're using a very low-level programming language like C, there isn't a linked list. You need to implement it. And how you do is something like this. So you have a pointer saying this is the beginning, and this pointer here is called next, and then you have your next, and then you have this is the end, right? What you need to do to include another one in the beginning. Let's say this is just storing numbers. So 8, 7, 6, you want to include 9 in the beginning. And you have a pointer for this, you have a pointer for this, and you have the pointers between them. So you basically have a link there. So you create another one. Let's say I just created 5 here. Right? My next, 5 next points to the beginning of the queue, or of the list. That's another operation. And then the beginning, I make the beginning point here. And then I have inserted one. Makes sense? That's the actual low-level operation that's going to take place for a linked list. Very interesting data structure. It's worth taking a look. Sounds good?
So, but how about if you want to, like, you got a collision, and then...
An actual collision like this. So actual collision.
So if you want to access, like, because they're storing in the same index, right? So if you want to access a specific node, then
Yeah.
how
Yeah, that's why collisions are tricky. So if you're asking the questions where TGT is, in O1, if your hash function is good, you say it's on the penultimate bucket. But from there, you need to iterate and check. Is it, and you start with the beginning. So the beginning is this one. Is this TGT? No. Next, is this TGT? Is this TGT? You keep asking until you find it, or you reach the end. And then you say, it isn't there, I add it.
Okay.
So worst case scenario, you need to iterate. So there's a better, where is it? Yeah, so basically, worst case scenario, you need to start here. So this is the beginning. So you can consider this actually as each bucket in the hash table. So you start here and check, is this one, and keep going. Following the links between the nodes.
So you need to actually store the key inside the node as well.
You don't need to store the key inside the nodes.
Otherwise,
For not all of them, at least. For instance, if you know, it's probably a good idea to store it, though. Yes, you need to store. Yeah, because this is basically giving you a index. So this is basically a number. Usually a hash will have a fixed size. So this is, let's say, this is 12, and this is TGT is giving you 11. And for collisions, you actually need to know the difference. But this is not a requirement, having where it is. This is blast specific.
Yeah.
Okay, thanks. Cool. Oh, this is fine.
So are there any like hash function that's especially like designed for bioinformatics?
Not for bioinformatics. There's hash functions
So
for
using-
a lot of data.
So it's like using hash functions as like, for example, the Python one, the built-in one.
For most cases, for most applications, the built-in
Is it-
hash function is really good.
Oh, okay.
Yeah. The problem is when you have trillions of things,
Yeah.
billions, and then performance deteriorates. Just because it's not expecting that much data or that many buckets. And
Yeah, because solving collision is really expensive, so a good hash function is really crucial.
yeah, and not sure. I think I had to use one. So when I was undergrad, I was working on spam detection. So collecting, well, the Brazilian network agency was putting proxies in the network just to collect spam. So the guy, a spammer would try to invade that, would manage because it's open, and we'll start generating spam. So, but the machine was actually collecting it. So we did that for a year. We collected 15 billion messages, something like that. And I needed to index them. I needed to index every single one of them, breaking them down in subject items. So I think it was my first paper, actually, identifying spam campaigns. So look and say, this is trying to sell this is phishing, actually, and this is coming from the same ISP or coming from the same country, and so on and so forth. So long story short, I had to index 2 billion, and it didn't work. And at the time, I think I tried 3 different programming languages, the built-in ones, didn't work. I ended up using a Google one, a Google version. At the time, it was just available and had been recently proposed. Don't ask me the name again, but yeah, you probably can find those that are tailored for specific problems. For instance, if you have way too many things to index, then because this is expensive, and solving it as well. So.
And the other question is like, I've kind of forgot about BLAST, but so it's like, so the input is like a sequence, and then you break it down into k-meres.
Yeah.
And then you look up the database for the k-meres, like, and then locate which sequence are the most similar ones.
Kind of. So BLAST is very. They divide it broadly in these steps. So basically, you have a query sequence, you have a database, right? And what you do is you pre-calculate your index for a database.
Yeah.
So for every single sequence, let's say you have the non-redundant and CDI database. You have millions of sequences there still. And you do k-meres on all of them, and you have an index. So each k-mere, where it appears everywhere. That's pre-calculated, good, so you do it once, and you have your query sequence here. So you have your query sequence, you do the indexing as well. But just to know how many different k-meres I have, so let's say out of 100, 20 are unique. I need to ask the question then, where those 20 appear to find these initial seeds.
To locate like what
initial
which
hits.
sequence is inside the database.
For instance, I think the size for the k-mere for protein is 11 residues, so it's quite a lot, so 11 residues there. So, and the principle is the following: if you find a hit that is 11 residues long, all then identical for local alignment, that's probably a good starting point. So you don't need. So the thing with BLAST is instead of doing this quadratically, it goes here. So, ooh, I can find this in O1 for a given pair, right? You can find this in O1, and then I just try to extend it until I can't anymore. And then it goes to the next one and keeps extending it. So this is the extend no gap version. So BLAST has the option to do with gaps, but the first one was just no gaps. So I just find a hit that's O1, and I just try to walk a little bit until I can't anymore.
How the extension works?
You basically go up and down the table. So instead of filling up everything, I'll fill up this bit, and since it's local, it's going to stop at some point. Let's say you do something like this, and it stops. And then I get this, you do something like this, and it stops, and like this, and stops. Instead of quadratic, it's a bunch of small linear ones.
So it's kind of like branch and bound? Like...
Kind of, yeah. But so instead of filling up everything, I'll fill up this region, this region, this region, this region, and then it returns to you the best pairs. Pairs? How do you call it? Best scoring pairs. This is not an alignment. So this extension was the best one, for instance.
Okay, cool.
Theoretically, it's the same complexity. Worst case scenario, you fill this all up.
Yeah.
But in practice, that's theoretical. In practice, it's orders of magnitude quicker.
Cool, thank you.
It's a very clever way to do it, though.
Yeah, it's very interesting.
That's very interesting. The guy was really smart, and he did it when nobody was thinking about it. That's why he deserved the 100,000 citations. 100,000 citations.
100,000?
It's more than 100. His name is Scholar. BLAST. His local, basic local. I can search too. So 79 on the first one, and then I think the next one is 30. So this dude here, So 150,000. Stephen Maltry. I was on a conference with him, but I didn't know who he was. But that's the 90s, right? Nobody was doing anything there. And he still published on a low impact factor. So this is 3, 4. And because of blasts, it's been keeping, so it's one paper keeping the impact factor of the whole journal. And nucleic acids research as well. But this is ridiculous. So 70